Webinar is going to discuss the normal EKG, otherwise known as the normal ECG. EKG and ECG are synonymous. The ECG is the English acronym for electrocardiography. EKG is the Dutch acronym. Often they use the term EKG because the first person to record the ECG on a human was a Dutch physiologist. So out of deference to his contribution to the field, often people use the term EKG. What we're going to get when we use an ECG is we're looking at voltage gradients that are created as myocardial cells sequentially depolarize and repolarize, that are the electrical activity created by this. It's transmitted up to the body surface where we attach these surface electrodes, which is then attached to a machine, and we can record this. And what you're recording is, or what you're going to be able to see, is it's going to indicate direction, it'll indicate magnitude of this electrical activity, and it's plotted against time. The ECGs do not record action potentials. What they record is total electrical activity that's generated by the heart. And just keep in mind why we're able to do this is that electrical activity that's created by the heart is transmitted through the saline solution. We're a big bucket of saline, which is a very good conductor of electricity. This is why it's transmitted up to the body surface where we put these electrodes. What we're going to be seeing, we're able to see, is we're going to look at the heart in multiple angles or views, and at any given point in time, and you can get a lot of information about the general direction of the activation of the heart during that specific period of time. Now, the ECGs that we do today is far different from what they did in 1902, which is when the first one was done on humans. So we'll show you a picture of what it looks like in a moment. But what types of information you can get from an ECG? What do they use it clinically for? One of the things it can do is it can show us problems with conduction. Is there a block in the conduction system going from the SA node to the AV node? Is the AV node not functioning properly? Is there a block within the Purkinje system? And believe it or not, many times in lab, we have detected problems with conduction in students at Parker. Another thing that the EKG is done or used for is to evaluate damage to the myocardium, extent, location of damage. So when you think about someone having a heart attack, EKG, they use that to figure out how bad it is, where it's located, so they can figure out what to do. It also can, you can have changes within the EKG if someone has hypertrophic changes in the heart. And we'll be discussing that in class. Another thing is certain medications may affect the electrical activity of the heart. And for example, like digitalis, if someone gets too much digitalis, it causes characteristic changes in the ECG. So they use that to kind of make sure they're not giving a patient too much digitalis. So they do very routine standard ECGs on someone receiving digitalis. Now, one thing though, keep in mind, the EKGs cannot give you any information about the mechanical condition of the heart, the contractile condition of the heart. It only can be used to evaluate changes within the electrical activity. So if you want to know things about mechanical condition, you're going to need to do other types of tests. So you're going to, you can do electrocardiography, you can do simple things as just measuring blood pressure and pulse. The mechanical condition of the heart's affected. It may affect the pulse. It may affect the blood pressure. So keep in mind, EKGs are only used to evaluate changes within the electrical activity of the heart. Now, the earliest EKGs were done where you can only kind of get just limited views of the heart. But what we're going to show you is that we're going to be able to get multiple views of the heart. And I want to just remind you about planes, which you learned in Try 1. We're going to be able to look at the heart on a frontal plane with some of the views that we're going to use, and some of them are able to look at the heart on a horizontal plane. So remember, you can only get limited information if you're looking at someone just in their face. Maybe there's something going on in their back. If you don't just look at their face, you're missing some very important aspects of that person. So what we're doing is we're kind of looking at the heart in multiple views or angles at any given point in time. So what we're going to do first is going to discuss the standard limb leads, which is what we do in lab. So the standard limb leads are called limb leads because of the idea that originally a patient's limbs were placed in salt water to get the signals, and what they called it was string galvanometer. I'm just going to show you a picture really quick. These were the earliest EKGs. So the limbs were placed, and it's going to be the very limbs that I'm going to show you. We're going to place these on in lab. Is they were placed in saltwater buckets. So this is why they call them limb leads. What happens is the standard limb leads, you have standard limb lead 1, 2, and 3, and you always use Roman numerals. You do not use Arabic for the limb leads. So it's lead 1, 2, and 3. Lead 2 is the one we use most of. 3 different views of the heart. With the standard limb leads, they are going to be measuring on the frontal plane. And with standard limb leads 1, you're looking at the heart going from right to left, and we can say in relative it's running about 0 degrees relative to the heart. With standard limb lead 1, you place an electrode, a negative recording electrode, on the right wrist, and you attach a positive recording electrode on the left wrist. The wire is what we are depicting here. Standard limb lead 2 is what we do most often in the lab, gives you the best pictures, or the best view of the heart. If you're just looking at very generically, it goes from the negative recording electrodes placed on the right wrist, the positive recording electrodes placed on the left ankle. The standard limb lead 2, you can say, is running about 60 degrees relative to the heart. Now standard limb lead 3, you have the negative recording electrode placed on the left wrist, and you place the positive recording electrode on the left ankle, and you get another view of the heart. Okay, it's going to be about 120 degrees relative to the heart. Now, so you get 3 different views of the heart measured on the frontal plane, and they refer to these standard limb leads as bipolar leads. Bi meaning 2, polar meaning poles. So the reason why they call them bipolar leads is that you have 2 electrodes placed on different regions of the body that each contribute significantly to the recording. Okay, so you have a positive recording electrode on one limb and a negative recording electrode on another limb. This is the one that we're going to do most often in lab. And what you've seen, what's been created, is they've created what we call Einthoven's triangle. In reality, when Einthoven was doing his EKGs, he viewed that here's the heart, and you had created a triangle. The heart was in the center of this triangle. The vertices of the triangle were created by the shoulders and in the pubic area. What he noticed, though, is you can move these things out to the limbs, and it didn't mess up with the recording at all. So you can have them up here on the chest and in the pubic area, but they moved it to the limbs, and it did not have what's the word I want? Didn't disrupt the recording very much. Now this, again, was to utilize the same placement of the electrodes that you saw for the standard limb leads. You have an electrode placed on the right wrist, you have one on the left wrist, and one on the left foot. Now the augmented leads are called unipolar leads because what the machine, this is what the machine actually does is, the machine creates a single positive recording electrode reference to a combination of the other electrodes. So somehow, and I have no idea how it does, the machine will combine, say for example, if I was going to look at this view right here, the machine combines the 2 electrodes, the one on the left wrist and the left ankle, is saying, okay, these are the negative recording electrode, and it's placed right here in the center of the heart. And then it creates this one positive recording electrode that's up on the right wrist. So we're going to be looking at the electrical activity starting from the center of the heart up to the right shoulder, and so they call it AVR, or Augmented Limb Lead Right, or Augmented View Right. If they want to look at the electrical activity of the heart going from center of the heart up to this angle here, the machine again combines the two electrodes in this type, the one on the right wrist and the left foot, creates that as a negative recording electrode right there at the center of the heart, and then creates that positive recording electrode on the left, and they call it Augmented View Left. And then you also can get one with looking down at the foot. Somehow the machine does this. I have no idea how it does it, but what you're doing is you're creating 3 more views of the heart. Now the augmented leads, they call them, one of the reasons why they call them augmented leads is the ECG amplifies the potential, so it makes it bigger so they can see it better. The augmented leads we will not be looking at all this trimester, but I have to just talk to you about them so you're aware that they're used. They get 3 more views of the heart. They're also measured on a frontal plane, okay? But they are considered, we call, unipolar leads, because somehow the machine combines 2 of the recording electrodes and creates them as the negative potential sitting there at the center of the heart, and the other one's a positive recording electrode. Now the last ones to talk about are the precordial leads. They're also called the chest leads or V leads. Now the standard ones that we use in a 12-lead ECG are V1 through V6. Okay, so we're looking at these ones. They're called chest leads because the leads are placed on the chest, and there's very specific anatomical locations where they must be placed. People go to school to be able to know exactly where these must be placed. Okay? Well, the precordial leads are different from the standard limb leads or the augmented leads in that these are measuring on the transverse plane. Okay, so they're looking at the heart a little bit different. They are unipolar, and the fact that what the machine does is you've got electrodes placed on the chest wall, but you still have those leads placed on the right wrist, the left wrist, and the left ankle. So the machine somehow combines the right, left, and the right and left wrists, and that left ankle, combines those leads together, creates this null potential, they call it, this negative potential, where it's right there at the center of the heart, and that these leads are the exploring leads. These are the positive recording electrodes. Again, I don't know how the machine does it, but the machine creates it. So obviously when Wilhelm Einthoven did his first ECG, he couldn't do any of this because he did not have these machines that could do it. What you'll notice though is that these leads, the V leads, V1, 2, 3, 4, 5, and 6, are going to be the best for looking at location, specifically within the ventricles. You're right over a certain part of the heart. The electrical activity you see is very much amplified because you're right over the particular area of the heart. So if there's something going on, say in the right ventricle, you're going to see it in specific chest leads, and specifically V1 and V2. You'll see the changes associated with what's going on in the right ventricle in these ones and may not see it over here. If you want to look at what's going on in the apex or septum, V3 and V4 are placed over that area of the heart. So these will be very good to evaluate changes or something going on within the apex or septum of the heart. V5 and V6 are the best to look at what's going on within the left ventricle. So these are going to be very good specifically for localization. So we will be discussing the chest leads. Although we will not do them in lab, it's going to be important to understand where those chest leads are placed and what it's used to evaluate when we look at abnormal EKGs. So when we look at the 12-lead ECG system, they call them 12 leads because you've got 12 different views of the heart. So the standard limb leads, you've got 3 views. With the augmented leads, you got 3 additional, so that's 6, and then you have 6 more on the chest. That's why it's called a 12-lead ECG. Just so, since they have the pictures here, if they need to, they can attach more electrodes along the patient's chest wall, or even along the back if they need to look at another part of the heart. But these are the standard placements for the chest leads. But keep in mind that even though I'm going to call this a 12-lead ECG, there's only 10 monitor leads that are required. So okay, let's think about it. Okay, you got 6 on the chest. So just think of it as wires. You got 6 on the chest. You've got 1 on the right wrist, 1 on the left wrist, and 1 on the left ankle. That's 9. Okay, where's 10? The 10, you have a ground that's placed on the right ankle. So remember the one that in lab that was the black one. There's a ground. So you have 10 wires, but you can get 12 different views of the heart. So what we're going to do is we're going to look at the normal ECG, why things look the way they do, what the normal value should be. So if you have that down, you'll be able to figure out what may be going on if some of those values change. So we're going to be looking at the various waveforms, so like the P wave or the T wave for the QRS complex. We're going to be looking at segments or intervals. Intervals always include a waveform and like a flat area of it. Segments are just flat areas. So when we're looking at the EKG, there's 3 rules to keep in mind. What you're looking at is the average current flowing in the heart at a particular point in time. It's the average. When you look, say, at the P wave, we've already known what the P wave is. That represents depolarization of the atria. You're looking at depolarization of both atria. When you look at the QRS complex, you're looking at depolarization of both ventricles combined. So it's combined electrical activity. Also, another rule to keep in mind is when you have current that's flowing, you will see deflections in this. So you'll see the P wave or this Q or the R. Current only flows if you're depolarizing or you're repolarizing. If you're completely depolarized, completely repolarized, you'll see just a flat line. Okay? So let's look at the standardization first. Okay? Normal standardization, you have, when you're looking at EKG, you have these grid lines. Okay? Standard paper, the machines run at a standard speed. If they change the speed, they must tell you. So it's very important that ECGs are standardized. So I can run an ECG in the United States, someone in Russia can interpret and get the same information. Okay? You're going to be looking at magnitude. So you're looking at, if you're going to look at magnitude, you're going to look at the y-axis up and down. We're going to look at timing. So you got to go at the x-axis left to right. We'll get information about timing. So here's the standardization. So each of these boxes is a millimeter. Okay? Each millimeter, and when we're talking about timing, represents 0.04 seconds. So every little square or millimeter represents a time has elapsed of 0.04 seconds. So if I'm looking at one of these big boxes, which has 5 boxes in there, 5 millimeters would be 0.2 seconds. Okay? If you look at the y-axis for voltage, the amplitude of the voltage, every millimeter represents 0.1 millivolts. Okay? That's the standardization. So for example, if I asked you what is the voltage of the P wave, you'd say, okay, it's 1 millimeter, so it's 0.1 millivolt. What about the Q wave? Here's the Q wave. That's a downwards deflection. That's one box. But since it's downwards, we're going to say it's minus 0.1 millivolts. Okay? What if I said, well, how long did it take for the ventricles to depolarize? So you should know that the QRS complex represents depolarization of the ventricles. So we're going to just, to make it a little bit easier, we're going to say it started right here in this line. Starting from here to here, there's 2 boxes. So 2 boxes, 2 millimeters. Each millimeter is 0.04 seconds. We'll say, okay, the ventricle is depolarized in 0.08 seconds. So this is where you need to start to kind of keep this in mind. You have to have those numbers down because those numbers are going to come up later. Well, why is the P wave upright? Why is the Q wave downwards deflected? Why is the P wave not as high in amplitude as, say, the R wave? These are some other things that we need to be aware of. When they did the EKGs, these are rules. Okay, these are hard and fast rules. Okay, so nothing's going to change this. Okay, so first thing, waveforms, how they look, depends on direction and magnitude. Okay, so first thing, if we say, have an example, we have a negative recording electrode, we'll say it's placed here on the right wrist. We have a positive recording electrode, say was placed on your left wrist. Here is my lead. Okay. If the wave of depolarization is traveling from running parallel to that particular view, that lead of we call it a lead of axis, okay, running parallel, you'll get the biggest deflection that you can possibly get. But before we even do that, let's first say, if that wave of depolarization happens to be running towards the positive recording electrode, your deflection will be upright. Okay, so that's standard. If the average direction of current flow is running towards the positive recording electrode, you're going to have an upwards deflection. If it happens to be running towards the negative recording electrode, you'll get a downwards deflection. Okay, that's easy enough. Now, why do we have these ones that are a little bit different in size? Well, size is going to be determined by relative direction to the lead of axis. If that wave of depolarization is running, say, towards the positive recording electrode, and it's running parallel, just like this, to the lead, you're going to get the maximum upwards deflection that you can get, the maximum recorded amplitude. As it's running away from parallel, it's a little bit smaller. Keep going, it's a little bit smaller. If it's running perpendicular to that lead, you may get a baseline recording, okay, where you're not recording anything, okay. We call it isoelectric or baseline. Or you might have what we call a biphasic or equiphasic recording, in that if I measured the voltage here and here and add them together, they'd add up to 0. Okay? So one of the things that determines the magnitude of the waveform would be how the electrical or the current is flowing relative to that particular lead that you're recording. Whether or not it's upwards deflected or downwards deflected is determined which is it running towards the positive recording electrode or the negative recording electrode. So in lab, you had a positive recording electrode on your left ankle. You had a negative one on your right wrist. Most of you, if not all of you, should have seen a pretty good upwards deflection, say for the R wave, okay? Because normally that electrical activity is running pretty much very close to parallel to that particular view of the heart, and it's running and it's upwards deflected because it's running towards the positive recording electrode. But there's something else that may play a role in the recorded magnitude, recorded voltage that you get. Timing is another one. Now, if you notice for the QRS complex, you look at the R wave versus the T wave. Both of them involve ventricles. This is depolarization of the ventricles. This is repolarization of the ventricles. Same amount of muscle that's involved. Okay, so I have to state that another thing that will determine the overall magnitude is the amount of muscle that's involved. So if you notice, the P wave is going to be way smaller than the QRS complex because the atria are smaller than the ventricles. Okay, so how much muscle involved will determine magnitude. More electrical activity is associated with more muscle mass, more recorded voltage. But what about this? Both of these are involving the same amount of muscle. So why is this recording voltage greater than the T wave? Timing. The ventricles depolarize much quicker than they repolarize because the cardiac conduction system's involved. So you have the Purkinje system that's involved in depolarization. So it's very, very quick. The repolarization of the ventricles does not involve the conduction system, so it's fairly slow. So that recorded voltage is kind of being extended out in the period of time. So overall, what you see is the amplitude is much smaller. But if someone sat there and tried to measure the area underneath these curves, they're going to be the same. So 3 things that can determine magnitude: the amount of muscle mass involved, how much time did it take, and the electrical activity. How is it running relative to that particular lead of axis, that view that you're looking at in the heart. So those things can determine the overall voltage that's recorded. Whether or not it's upwards or downwards deflected is determined by, is it running towards a positive or a negative recording electrode. Okay, so let's kind of go over a couple things and why they look the way they do. So when I'm going to show you, we're going to be showing you pictures. I'm going to have these red arrows in there. So I got to describe to you what vectors are. You should actually already know what vectors are because you should have learned it in Try 1 in one of your radiology courses. Well, vectors are often used in physics. Vectors give you information about direction and about magnitude. When we do a vector, the kind of pointy end of the vector is always the positive end of the vector. This part is the negative end of the vector. Okay? The length of the vector that I draw will give you information about magnitude. How much electrical activity is involved. Bigger the arrow or vector, more magnitude. The pointy end of the vector, the arrow, points in the average direction of current flow. So if I put a picture of the heart up there and I have an arrow on there, I'm showing this is the average direction of current flow in that particular area of the heart, which will determine what that particular waveform will look like. Okay, so let's look at the P wave. And what we're looking at what you'd see in a lead 2, because lead 2 always gives you the best looking waveforms. Okay? So, vector associated with the atria. This is showing you the average direction of current flow within the atria. You notice a little bit to the left, just because, remember, the left atria is going to take a little bit longer to depolarize because the electrical impulse originated in the right atria, but it has to travel over to the left atria. So the vector is always going to be pointed a little bit in the part of the heart that takes the longest to depolarize. Okay? So we have this arrow. It's pointing a little bit, it's pointing kind of down and a little bit to the left. This is where we place the recording electrodes for standard limb lead 2. You'll notice the P wave is upwards deflected because the arrow is pointing towards the positive recording electrode. Okay? P wave's not so big because not a lot of muscle mass involved. I mean, the vector is running pretty close to parallel. So, I mean, but what you get, though, is because of the not as much muscle mass involved, as well as the fact that the atria take longer to depolarize than the ventricles, that P wave's a little bit wider than if you compare it to the QRS complex. So the P wave is smaller in amplitude than the QRS complex because it has less muscle mass, as well as it takes longer to depolarize. That's why it's a little bit wider. Okay? It's upwards deflected because the average direction of current flow is running towards the positive recording electrode. What about the QRS complex? Well, let's do the Q wave first. Q wave is this small downwards deflection that you may get on the ECG. It represents depolarization of the septum of the heart, and this is showing you the average direction of current flow in the septum. Why is it negative or downwards deflected? Because it's running towards the negative recording electrode. Why is it so small? Muscle mass, not a huge amount of muscle mass. Some of you may not even see a Q wave. There'll be plenty of you that will not see a Q wave when you do standard limb lead 2. Doesn't mean the septum didn't depolarize. What's the other way things look the way they do? Is how that electrical activity, that vector, is running relative to the lead of axis. If you notice here, that vector is running pretty close to parallel. So in some of you, your hearts may be sitting just right in your chest wall, that vector runs perpendicular to that lead, and you won't see recorded voltage. Okay, so Q wave is very small because not a lot of muscle, plus the fact it's running pretty close to perpendicular. If you don't see a Q wave, it is running perpendicular to the lead. Now the R wave is the big one. You can't miss the R wave. R wave, big, we got a lot of muscle. This represents most of the muscle fibers in your heart, from apex up close to the base. So it's the majority of the muscle fibers within the heart. It's upwards deflected because we're running towards the positive recording electrode. It's big because you got a lot of muscle, plus it's running pretty close to parallel to the lead of axis. Okay. Now even though I don't have it, the S wave, if I follow with the S wave, it's downwards deflected. That represents the current that's flowing up here at the muscle fibers at the base of the heart. And the vector would be running towards the negative recording electrode. That's why it's downwards deflected. And there's not a lot of muscle involved, so that's why it's a pretty small waveform. If you don't see an S wave, you're not dying. It's probably the current flow is running perpendicular to the particular lead of axis. Okay, so don't be concerned about it. So I just want to show you, if you kind of have a basic idea of how things are going to look the way they do, if I drew a heart and showed you where we placed the electrodes, and I said, okay, this is, and I put a vector, how do you think that particular waveform would look like on an ECG? So if you look at these, we've got 5 hearts doing a standard limb lead 2, and I'm drawing different vectors. So you notice this one, you got the most upwards recorded voltage being recorded because it's running parallel to that particular lead of axis, and it's running towards the positive recording electrode. This one is not as big because it's starting to run away. This one's pretty much perpendicular, so this one is a biphasic or equiphasic one, or we could have had a baseline recording. These two are negative, downwards deflected waveforms because the vector is running towards the negative recording electrode, and the one that gives you the most recorded voltage would be the one again that's running parallel to the particular lead of axis. Okay, so kind of have an idea about that is important, because sometimes we may see something like inverted P waves. Say, wait, I'm not supposed to see an inverted P wave. That may happen. As long as you know you put your electrodes on correctly, it can indicate something's going on in the heart. If we go over what certain voltage should be, how it should look. If it doesn't look that way, then you need to start figuring out what may be going on. So let's go through the different various waveforms and segments and intervals. Would you have a table in your notes? It's a very good idea to review that table in the notes. Have it down, because once we start doing abnormal, you need to have the normal in your head to be able to understand the abnormal. Okay? So let's do the P wave first. P wave, you already knew, represents depolarization of the atrium. Okay? It's upright in your leads, usually positive. Okay? Shouldn't be more than 2.5 millimeters in height. Okay? If we want to do voltage, that would correspond to 0.25 millivolts. Shouldn't be more than it shouldn't take more than 0.11 seconds for the atrium to depolarize. If it's not upright, if you get notches in the P waves, if it's too wide, that may indicate problems with the atria, either conduction, maybe hypertrophy, things like that. Okay, so those are your normals for the P waves. Now, the PR interval corresponds to beginning of your P wave to the beginning of your QRS complex. Okay, so I have to emphasize again, beginning of the P wave to the beginning of the QRS complex. If you do not have a Q wave or an S wave, we're still going to call it a QRS complex. Okay? If you have a Q wave, you would go beginning of the P to beginning of the Q before we move away from baseline. If you don't have a Q, we go from beginning of P to the beginning of the R, again, right before it leaves baseline. What that tells you, it tells you the amount of time it takes for that electrical impulse that originated from the SA node to make its way to the ventricles. That's what the significance of the PR interval is. So if you know the normal range, it should take anywhere from 0.12 to 0.21 seconds for that electrical impulse to go from SA node down to the ventricles. If it's greater than that 0.21 seconds, we're going to refer to it as a first degree AV nodal block. Okay? There's a term. We're going to be talking about other type of AV nodal blocks. The PR interval is often used to evaluate conduction through the AV node. The AV node is very susceptible to disturbances. If you disturb the blood supply to the AV node, you can get problems with conduction. So that's a very common thing that we see. So normally 0.12 to 0.21 seconds. If it's less than that, there may be an issue. More than that, there may be an issue. And we're going to be talking about that in lecture. Okay? The next one is the QRS complex. Okay? So you already knew the QRS complex represents depolarization of the ventricles. Okay? But all of these are examples of a QRS complex. So here's your standard QRS complex. Some people don't have a Q. Some people don't have an S. Some people have what we call a QS. Some people just have an R. And some people have what we call, well, there could be multiple variations. This is a QRS, R prime, S prime. R prime, if it goes back above baseline, that's an R prime. If it goes back below baseline, they call it an S prime. I've actually seen R double primes and S double primes where if it went up again. I refer to this as the bunny ears. All of these may be considered to be normal as long as the duration of that complex is fine. So even having these bunny ears may be perfectly fine if the duration is fine. So here's the duration. 0.06 to 0.09 seconds. That's how long it should take the ventricles to depolarize. If you remember the lecture on the cardiac conduction system, I had said that generally the ventricles will be completely depolarized in 60 milliseconds. Here, you got the 60 milliseconds. We're giving you a little bit longer, get a little bit more leeway for the normal variations in the population. So anywhere from 60 to 90 milliseconds, which is 0.06 to 0.09 seconds, is completely normal. QRS complex, if the duration is abnormal, it can tell you, one of the things it can be used for is to evaluate conduction through the bundle branches or the Purkinje system. I mean, bundle branches are part of the Purkinje system, since the Purkinje fibers allow that the ventricles to depolarize at such a very fast rate. So if you've got problems with conduction within the Purkinje fibers, the QRS complex may be prolonged. Later lecture we'll talk about voltage. So right now don't worry about voltage, but here we're just talking about duration. If that QRS complex is longer than 0.1 to 0.12 seconds, they call it an incomplete block, and we call it incomplete block within the Purkinje system. If it's greater than 0.12 seconds, they will refer to as a complete block of conduction within the Purkinje system. Okay? Now, following the QRS complex, say right there, or let's go back, here, 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 that's referred to as the J point. Okay? J point is a very important reference point. This is the point where, again, the QRS complex returns to baseline. This point, it's no current flowing, it's zero potential, it's always zero potential. The ventricles are completely depolarized. We have not started to repolarize, so there'll be absolutely no current flowing at any point in time. No matter what's going on in the heart, this is always zero potential. I don't care where this is on an ECG. The end of the QRS complex at J point is zero potential. So this is always going to be very useful for a reference point. We're going to use this when we look at a couple other things. Okay, so let's look at from the J point to beginning of the T wave. That is referred to as the ST segment because this was the S, this is the T. They call it an ST segment. ST segment is from the J point to the beginning of the T wave. It should be isoelectric or zero potential, but you're allowed, it may be a box above or below this J point. Okay, so you're allowed a millimeter, or we can say it can be up to 0.1 millivolts or minus 0.1 millivolts and still be considered okay. Okay, that's normal variation. But if it's more than that, we're going to refer to it as an ST segment shift, or they refer to it as a current of injury. And we'll be discussing that in lecture, specifically in lecture. So right now, that thing, you're allowed a little leeway there. If it's shifted, it can indicate you may have ischemia going on in the heart, an infarction has taken place, you can have inflammation of the pericardium, pericarditis, and so this is something that I'm going to be the most concerned about if I see a shift in the ST segment. Now, following the ST segment, you'll have the T wave. Well, oh, sorry, let's go back. Well, since we're here, let's do T wave. Now, the T wave represents repolarization of the ventricles. You already knew that. That's not very symmetrical. It's like usually a little asymmetrical. In most leads, it is positive, but it doesn't have to be positive or upright in all the leads. It can be inverted in standard limb lead 3, and you may also see it inverted in your V1, your chest lead V1, and not be concerned about it. The voltage, it shouldn't be more than 0.5 millivolts or 5 millimeters in height. Okay. Certain thing we'll be going to kind of briefly go over some T wave abnormalities, but it's not supposed to be more than 0.5 millimeters or 0.5 millivolts. It's upright in most of your leads. If it's inverted, one of the things that may cause the T wave to invert is if repolarization was slow. So it's one thing that could cause an inverted P wave or T wave. Now, following the T wave, you have what we call a TP segment. The reason why I'm mentioning this, it goes from the end of the T to the beginning of the P. Like this ST segment, the TP segment should be isoelectric. It should be baseline. Okay? At this point in time, the ventricles are completely repolarized. They have not started depolarizing. Nothing's depolarizing. No current should be flowing in the heart. If this, but you're also going to allow a variation, just like the ST segment, of a millimeter above or below the J point. When we look at myocardial injury and ischemia, and that in lecture, I'll be discussing why you want to look at that particular segment more than the ST segment to evaluate if there's any current flowing in the heart when it should not be. Okay. You also have, we mentioned the T wave. I'm going to show you some T wave abnormalities. Okay. You may have very tall peak T waves. We said it's not supposed to be more than 5 millimeters. If it's more than 5 millimeters, it can indicate hyperkalemia, get too much potassium. The T wave may be inverted if you've got ischemia within the heart, but it may also be inverted in other conditions. It's not, an inverted T wave is not characteristic of ischemia, but you may see it with ischemia. You may have a small T wave and a larger U wave with hypokalemia. But again, this is not diagnostic of hypokalemia. Okay, so T-wave abnormalities generally are not diagnostic of things. You need to look at other information to be able to figure out what's going on. Okay, so but you can have various T-wave abnormalities in certain conditions, and we'll cover some of those when we do some abnormal ECGs. Now, one of the last things is the QT interval. QT interval goes from beginning of the Q, if you don't have a Q, would begin beginning of the R, to the end of the T wave. So the QT interval, why they call it an interval, is it includes a waveform and a segment. That's why they use the term interval. The timing of the QT interval will depend upon your heart rate. Okay, so it's variable. Certain conditions, though, can lengthen or shorten the QT interval more than it would be associated with changes in heart rate. For example, if you have hypercalcemia, too much calcium in your blood, it can shorten the QT interval. Hypocalcemia can cause a long QT interval. Okay? Now, in your notes, it may mention that the QT interval represents time period of ventricular contraction. Not completely, because the ventricles don't really contract until we hit the peak of the R wave, but it does have an idea of give you an idea about the time period of ventricular contraction, because you're going from R to here, the ventricles are contracting from that period of time. Okay. Now the last one is the U wave, and U wave, we said we could have seen it with hypokalemia, but they call it a wave of unknown origin. It does not necessarily indicative of hypokalemia. Usually, if you start seeing it, may indicate maybe part of the ventricles are taking a little bit longer to repolarize, or a little slower than normal, but again, not very indicative or diagnostic of certain conditions. Now, last topic I want to look at is the idea of refractory periods when we talk about the heart, is the difference between an absolute refractory period and a relative refractory period, and compare it to what you see in skeletal muscle. The absolute refractory period refers to the fact that if I stimulate that muscle, again, no matter what the strength of the stimulus is, you'll not be able to get it to fire again. So in cardiac muscle, from the beginning of the Q to beginning of the T wave, if you try to stimulate that heart again, it won't do anything. Okay? The absolute refractory period, it's much longer in cardiac muscle than it is in skeletal muscle, which is going to be real important. Now, the relative refractory period in cardiac muscle is a period of time. It starts from the beginning of the T to about 3/4 of the way into the T wave. If you apply a stimulus to the cardiac muscle again, you could get it to fire again, but it's got to be much stronger than normal. Okay? Well, when you compare, see if I have my picture here. If you compare skeletal muscle versus cardiac muscle, if you look at absolute and relative refractory periods, these are much longer than in skeletal muscle. So what's so important about that? Why should you remember that? Cardiac muscle cannot be tetanized. Okay? Tetanized cardiac muscle would not be able to pump. Skeletal muscle, we have to reach tetany to be able to generate the tension we need to do its work. Skeletal muscle can be tetanized. You apply stimulus repeatedly, and you get the increased tension development. Cardiac muscle cannot be tetanized, because tetanized cardiac muscle would not be able to pump. It wouldn't be able to fill up with blood and be able to pump. So the refractory periods are much longer in cardiac versus skeletal muscle. Also what you'll notice is cardiac muscle contracts a little bit longer than skeletal muscle, because what it's doing, it's got to pump that blood out. Okay? One thing that may not be in your notes, might be a good idea to write down, is the refractory periods in atrial muscle versus ventricular muscle. They're different. Atrial muscle's refractory period is less than ventricles. Okay? slightly less. That's why atrial rates can be much faster than ventricles, which is one of the things that we may be discussing when we look at abnormal ECGs and arrhythmias, that the atria could, if they were kind of atria and ventricles were not pumping coordinated in a coordinated fashion, atria can get to much faster rates than the ventricles because its refractory time is a little bit longer. So, or not longer, it's shorter. So having the refractory rates the way they are, it does limit heart rate. So if you have a longer refractory period, you're going to have a slower heart rate. Okay. So this is going to be the last part of this lecture. During class, we'll discuss some abnormal ECGs. So if you know the normals and what each thing represents, when we discuss abnormals, it will not be very difficult at all.